Let's solve the problem that has 3 pumps. Here's a pump 1 and pump 2, and they're in a fluid system. They're in parallel. And then they join together the output of pump 1 and pump 2, and they go into pump 3. And then that goes out through the system, which comes back and then splits and goes into pump 1 and pump 2, either pump 1 or pump 2, and then continues. Okay, so this is a problem in our textbook. For each of these pumps, they give it the specs. So pump 1 is a 1 by 1.5 by 8 inch pump running at 3,500 RPM with an 8-inch impeller. So can you find one of the handouts that I gave to you for that pump? Can you find one of the 3 pages will be 1 by 1.5-8 running at 3,500 RPM. In the bottom corner of that page, the bottom right, it's CDS 5008-1. Is that it? Everybody found it? On your page, put pump 1 somewhere prominently in the upper corner somewhere. So we know this is the characteristics for pump 1. Now the second pump, pump 2, is a 2 by 3-10 at 3,550 RPM, and it has an 8-inch impeller. Can you find that one? And it's 3,560, okay, 3,550, 3,560. I'm not going to make a correction on that RPM. The bottom numbers in that one, CDS 5024-1, right on it, pump 2. So that's our pump 2. And then the last one is pump 3, and it's a 2 by 3-13. It's 1750 RPM, and it's a 10-inch impeller on it. And do we find that curve? Okay. And what is the corner? It says CDS 3832-3. Okay. So you got your 3 pumps. And you could look at the range of flows in GPM. So everything is going to be flow in GPM, and then the head gain across the pump, they don't literally specify it, but on the y-axis, it's feet. It's in feet, so you can write that in. Now the system that they hook up to is characterized by the equation that H across the system head loss is equal to 120.0 plus 0.016586 Q to the 1.7, I can't read that number, 5 or 3, what is it? 7.3. And what it is the units work such that you feed it GPM for the flow rate, and it returns foot head loss in the system. Somebody says, I'd like to not work with elevation head, I'd like to work with energy head. It's going to be exactly the same in units of foot pound force per pound mass, numerically the same. But we're going to work just in feet. True? Okay. So if you plotted this, what does this plus sign make this curve for the system head look like on a plot? Something that starts at 0, well, it doesn't start at 0, does it? Yeah, it does. No, it starts at 120. Doesn't it start at 120? And then it has a quadratic nature to it. Okay? It's close to quadratic. The coefficient is about 2 on Q. That's our system. Well, what you can do is you could take the system curve for pump 1 and the system curve for pump 2 and conceptually combine them. Now, let's go ahead and just quickly sketch on one plot. I know they're on separate plots. But tell me, what is the range of Q that I should use if I want to put pump 1 and pump 2 on the same plot? What should Q, the x-axis, range from? 0 up to what? Look at your plots. 0 up to what? What will be the maximum Q to make sure and capture both? How many GPM? 300? 200 GPM will cover both of them. So let's do up to 200 GPM. There's 100. There's 50. There's 150. What about the y-axis? The head. Pump 1 and pump 2 I want to show on the same plot. What should be the maximum? But what about pump 2? I want to show it on the same plot. Okay, you're right. You're looking at, we should have done this. On pump 1, take and remember what curve of these pumps are we going to use? We're going to use the 8-inch impeller. Highlight that line. Isn't that the topmost curve in this sequence of curves for pump 1? Highlight it so that we know that that's one we're working with. That's our actual pump 1. It's one of these impellers. Now let's go to pump 2 and say, okay, which impeller did we use for pump 2? We didn't put in the biggest impeller, the 10-inch, it's the 8-inch. So highlight that line. So if the maximum for pump 2 is 300 foot, what about pump 1? Around 300 foot, isn't it? So we want to maybe stop at 350. Let's put 300 here. And there's 100. Not 100, come on now. Let me try and draw this accurately. That's what I'm trying to do. Okay, 1, 2, 3. So there's 300, 200, 100. Now, just roughly sketch out on the plot, what does pump 1 curve look like? It ends at around 200 GPM. At what head? Around 225. So it's probably right there to right there. There. Would you say that's a good looking pump 1 curve? Okay, now what about pump 2 curve? Well, it's a 8-inch, so it starts at just a little bit below. Let me change color on it, put it at this color. And if I look out, what about, it goes out to 500 GPM. Hey, did we put this on a large enough scale? How come somebody told me to stop at 200? 200, 300, 400, 500 GPM. It should be out to like 550, 600, right? So now I want to sketch that curve on this same diagram. And if I go out to about 500, it looks like it drops down to about halfway between 150 and 200. So goes out to there. What did I say at the 500? It's right around there. There. I know there's some curvature to it, but isn't that pump 2 curve? So now they're on the same diagram. So when you combine 2 pumps in parallel, what does the composite look like? It's as if the Q through pump 1 and the Q in pump 2 add up, but they have to have the same head gain across pump 1 as the head gain across pump 2. They're not going to have when it's running at steady state, the head gain across pump 1 has to equal the head gain across pump 2. True or false? Yeah, it's true, right? But then the net flow by an equivalent combined pump 1 and pump 2 that are physically in parallel, but the equivalent one would simply have the sum of the Q's for each of the head. So the combined would take this red curve and this purple curve and really not change their height, but make it stretch out further. Make sense? The composite curve, I don't really want to show it, but it's something like, maybe I'll just sketch it. It'll go like this, further out. It's like adding the 500 maximum with the 200 maximum, but it has to match up at the same heads because you're drawing lines across a constant head and then add them together. All right. Now the other one is easier. What about pump 3? It's in series with the other pump. So it doesn't like stretch the combination, it actually adds height on the HQ plot. So it adds height. Let me do this. This was pump 1. Is that true? No, this is yeah, that is pump 1. Pump 1. And we were running with this one right here. Okay. And then this was 24, that's pump 2. Pump 2. And we were with this one right here. True? All right. And then pump 3. Pump 3. And what do we have for pump 3? It's a 10-inch, so it's that one right there. All right, well, first of all, can you see from the diagram that the Q, the sum of the two Qs right here, has to go through pump 3? So do you think that both of them are going to be, the sum will be up in the 500 GPM range when pump 3 really doesn't want to take up the 500 GPM? Do you see that? I mean, so it's probably going to be operating where the net flow through pump 3 is below 500, below 400, somewhere in there. Okay. But when it's operating, the pump is going to be adding, let's just say 100 foot of head for pump 3, right? So if it's operating at, 300 GPM, then if I look at it, let me go back to this diagram. Both of these have about the same head. It's just the flow is stretched. If I had to guess, I would say pump 2 is like double pump 1. So if I just had to guess, I would say the flow through pump 2 is double the flow through pump 1. And if I had 300 GPM going through the combination, if I had 300 GPM going through, then what's going through pump 1? 100. This is just guessing. And what's going through pump 2? 200. True? Now, you could check that guess and see if it's going to work. Let's just run some numbers by hand. Somebody says, yes, the Q here, let me do this, reuse this illustration right here. Come on now. Erased too much. This Q1 we said was 100 GPM. And this is 200 GPM. Now, let's just go check. At 100, what's the head loss? Or the head gain, sorry, this is a pump, not a, so it's right in, what number is that? 285. Everybody gives it a thumbs up? Right. And at 200, what is the head gain? Hey, it looks like 285 foot of head. That's great, it has to be that way. And then I come over here, I have at 300, what's the head gain? It's about what? 85. 85. So now I come back to my illustration. We're going to do this in a computer code, but I want to do it by hand first. What did we have? We had a head gain of 285 and 285. And then what about the head gain for pump 3? 85. So we have 285 plus 85. What do you get for the net head gain? 370. Okay. So guess what has to be the loss across the system? 370. Let's just see if we just by eyeball balance the system. What is our actual head loss when Q is 300 GPM? Somebody will have a calculator. You want to run that? So for our head gains from all the pumps was around 370 foot. Now what is our head loss through the system if it's actually 300 is the balance. If it's 440? How many people agree? Thumbs up if you agree. That's what you got? All right. So it's not balanced, is it? What's going to actually happen to this system? Is the flow going to be higher or is the flow going to be lower to balance it? I mean, this is just the,
So we need to decrease the flow, right?
You think that the balanced flow will be lower than 300 GPM? How many people need more time to think about it? Or is it 300? Look like 300. Looks like 300. Okay, I'm going to tell you that we are not too far off. The final is 262 GPM. Somebody says, check me on that. Okay, well, what I'd do is I'd come over here and I'd say, I don't, let me do this first. I would do right here, I'd say, give me 262 somewhere in here. That's 250. Right there is 262. Come up, hit right there, and read off the head that is gained across that third pump. And what is our head gain across that third pump? Can you read that? It's 90 what? Okay. I want everybody to do it on their illustration. I want you to do it on your illustration. So how many GPM? 262. And what is the head? And I want it good to 2 digits. So there's a difference between 90, 91, 92, 93, 94, 95. Okay, somebody suggested 95, but I really want to see what you can come up with a little closer. Or it could be 89, 88, 87. So at a GPM of 262 for that curve, somebody, are you still with 85? Or are you going to go with a different number? You got 90? 92? All right. I got head gain of 91. 91. How many people agree with that head gain of 91? Pretty good. How about disagree with more than 2 or 3 foot of head? Nobody? Everybody was that close? Off by 4? That's pretty good. Well, all right. Now that we know that 91 foot of head is dropped or gained, about the third pump, then, and the total flow is 262, we know the head drop of the system. The head drop of the system is 374. So there's this head loss is 374 foot. Just use that equation, plug in 262 for Q. And now I know that the head gain is not 85, but it's 91. So what has to be the head gain across both pump 1 and pump 2? Just do the subtraction. 374 minus 91. True? Isn't that it? And what do you get for the head gain that has to be across both of those pumps? 283. Head gain is 283 foot. Let me ask you, has to be the same across pump 1 and pump 2? Or can the sum of pump 1 head gain plus pump 2 head gain equal to 283? Don't get messed up on the series and parallel, right? They're not in series, they're in parallel, the same head gain. Okay, now that we know the head gain of each of these pumps, we come over here and we say, where is 283? 283. Not very far different from 285, was it? But you could do it much more accurately, and you would find that the flow through pump 1, somebody want to just run a number on it? I'm going to pause. I want you to do it. All right, so for pump 1, the GPM, I came in right at 109 GPM. If you like that, give me a thumbs up. Very good. And thumbs down from, sorry. All right, now let's go to the next one. What was the head gain across the pump 2? I want to get its flow rate. You're doing the same thing. It's not 285, it's 283 foot. So then we come across and have to read off. And when I read off that GPM, we're kind of bouncing around here. We know that I gave you the total flow rate. So the total flow rate here is going that way, right? Yes. And so then I know the head gain across pump 3, and I know the head loss across the system. So that allowed me to calculate the head gain across each pump 1 and pump 2. Then I went back to the pump curve to get Q1 and then Q2. Actually, what you can do is you can now just, maybe what you're saying is, isn't Q2 equal to Q3 minus Q1? Yeah, they have to be consistent.
No, I'm saying, should we divide that to 150?
Oh, yeah, that's the question I was asking is, this is the head gain across pump 1, that's the head gain across pump 2, they have to match. They have to both be 283 foot head gain. We calculated Q3 to be 262. We just did Q1 to be 109. You find that the Q2, just by volume balance, is 153. Let's look at that second pump. 153, you're right in this vicinity. Do you really want to be running that pump at this vicinity? Not really. You really don't. Can you tell me, okay, so this is the operating point for that pump. Can you tell me the efficiency at that operating point? Okay, you're generous at 55%. That's highest. That'll be a little bit below 55, right? Maybe 53? Okay. So the efficiency at that operating point is 53%. I should have done that because we're going to need it. Let's go back to this pump. This was 110. That's kind of in this vicinity, right? Come up. It's right around here. What's the efficiency for this pump when it's running? 57, 56. I'd pick 56, be little, but it's closer, 56 and a half, 57, somewhere in there, right? And then the third pump, we already said it was running at 262, and that's so it comes up right here. What's the efficiency at that point? 64%. 64%, right? I think I picked 63 in my calcs, but that's okay. I can update it. But 64 looks good. That's efficiency. All right. Now, you come back to this problem. I didn't say how I got the 262 yet. I'll do that in a second. But they ask us, the question in the textbook is once you've calculated to find the operating point for each of the pumps, we just did that. We found the operating point for each of the pumps. Get the efficiency for each of those pumps. And now find the power required for each of the pumps. And they give you the fluid density. So they give us, if it was water, it'd be 62.4, but they give us a value of 53.7 pound mass per cubic foot for the fluid density. So if it's operating at this point right here, that's the operating point for pump 1, what is the power having to be supplied? Now, if it would be water, I could just look and say, okay, it's a little bit below 15 horse and a little bit above 10 horse, and I'd visually interpolate, right, for the power to supply it. But it's 62.4 is the nominal density for water. So it's let's do it using the efficiency and the density of this actual fluid. So what would be the power, the brake horsepower? It would be the fluid power divided by the efficiency. Well, how do you calculate the fluid power? That's exactly right. So you have either the cap H head gain, energy head, times the mass flow rate, or you have the pressure gain times the volumetric flow rate Or you have the elevation gain. I'm trying to drill this into you, right? 3 ways of writing it. Elevation head gain times, it's kind of the GPM. What is that? Is that a volumetric flow rate? Yeah. But you really need to do, for this mass flow rate, this is probably the most convenient right here. Put a Q right here for the volumetric flow rate. Put a rho right there for the mass density of the fluid. Now that gives me the mass flow rate. Multiply by cap H, but luckily the numeric value of lowercase h in foot is exactly the same as cap H in foot pound force per pound mass. True? Numerically, so that's easy. So use this equation right here. We can get then for this fluid density, which is not 62.4 but is 53.7, we can get the brake horsepower for the first pump. I'm going to pause. I want somebody to run on their calculator that calculation. You're going to have to convert gallons, 1 gallon, no, 7.48 gallons is 1 cubic foot, true? And you're going to have a minute at 60 seconds. And there's one other conversion factor. 550 foot-pound force per second is a horsepower. And you got 12 horse? Excellent. It's right at 12, yeah. That's it. Thank you. All right. Now, how did I actually do this? I think the rest of this problem, you can get the power for each of those other pumps. But how did I actually do it? Well, this is the way you do it. First, you have to analyze the pumps. And just like the system curve was given as a quadratic that we actually plotted, it goes up, you really need to get a pump curve for each of those pumps. If you just focus on pump 1 right here, what I did was I said, okay, go and pick off values. Easy one is Q is 0. Where does it intercept the y-axis for pump 1? Then I came out and I picked off some other values. And so I'm going to curve fit. So these values are pairs of Q, and head for the pump. Can you verify some of those? Usually this one was the last one. It's where the curve ended. Okay. Then I say I'm going to fit a parameter A, B, and C where I'm using a quadratic equation. But you can see that the quadratic equation I want is just going to be A minus C times Q squared. That's the one I'm going to use. What happened to B? I just set it to be 0. It really didn't improve the accuracy. And so it's a quadratic down curve for the pump performance curve. So that's what I fit. So this parameter is my A. I could have started with the parameter 100 guess. And this one, 2.02 times 10 to the minus 3, it could have been some other number. I'm not going to change it. Let me just do this. I'll copy, paste it. Now let's do this one, 0.001. Well, if I come over here and I say, if that A and that B, I can actually get a head curve estimate and compare it with what I read off of the diagram. This is using my curve, the polynomial. See how it's used? You just say the Q, well, first of all, A minus, well, forget the second term. I got rid of it. I tried it and it didn't help. A minus C Q squared. You see it? Yeah. And so then I just got that embedded once and I dragged that down. And then I compare each of these curves. I should change the format on that, make it a little easier. Not scientific. Number, too many digits. Whoops. Maybe like that. Okay. So you can see with these two values, but if I change that one, maybe I make it 0.00002. Well, it doesn't improve it. So this is the difference squared between, so I'm going to do a least squares minimization. So then this one is the same thing. It's the difference squared. I sum them up. Now I have that to drive to 0. Do you see that? So if I want to drive that, if I want to minimize it, I can't get it to 0, but it's a curve fit. I can try and get it close to 0. I want to minimize that error. So what do? I vary that parameter, and I vary this parameter to drive this one as much to 0 as possible. And so we go under Data, go under Solver, and we set this up. And so we say, this is my objective. Set this objective to E13. I could try to maximize it. I could try to minimize it. I want to minimize it. And I need to change variables. Which variables do I want to change to minimize that objective function? I'm going to change that cell, comma, and that cell. So 2 cells it's going to work on to try and change it to minimize. And you cross your fingers. It never works the first time, but I worked this out before class, and there it is. Now, this number is 306.5217, blah, 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 blah. So what I did was I looked at this number. Maybe I copy it, copy, and then paste the value. Paste this value so that I have this number right here, right? Now, if I say, I don't think it's much different between 307, see if that number really changes much. So, you know, by truncating that number, rounding off the first number, it didn't change it much. I don't want, you know, I felt ridiculous looking at textbook. That coefficient in front of the Q to the 1.73 is 1, 2, 3, 4, 5 significant digits. You really think 5 significant digits are needed? That's not needed. Likewise, right down here, there's so many significant digits to this number. I just said, round it off to 2.24 or something like that. I even watch how much it changes. It doesn't change much, does it? So even here, I think I got rid of the 4. Close enough. Good enough fit. True? Well, you have to do that for pump 1, then you do it for pump 2. There's our coefficients. And then you do it for pump 3. A lot of work to get it fit. But once you have that, now let's balance the system. So on a different sheet, what we do here is I put in the mass density. I had to put it in somewhere. But I think of leg 1, leg 2, leg 3, and those are going through the pumps, and here are the copied over coefficients for each of those pumps, the A and the C coefficients. And so I didn't know this. I shaded these 2. These are going to be iterated on. Maybe I start and I say, I think it's 100 GPM in 1 and 100 GPM in 2. That's initial guess. Well, that's going to force 3 to be 200 GPM, right? Because Q3 is the sum of Q1 plus Q2 in our network. And so I didn't iterate on 3 Qs. I just looked at, I'm going to iterate on 2 Qs. And then I know the coefficients, so I get the head gain for each of these pumps. First of all, that's close to that one, but they're not exactly the same, so it's not really balanced. But then I add they're supposed to be balanced pump 1 and pump 2 head gains. Then I add it to the pump 3 head gain, and that should equal the system loss. Well, the system has to take what goes through pump 3. Here's the system coefficients. There's the system head loss. Okay, so what do? I come over and I do loops. Kirchhoff's loop laws, right? So instead of voltage gains and drops, I'm doing head gains and drops. True? Just like what we did. So the first loop, think about it. Let me go back to the illustration. First loop, go through pump 1, then through pump 3, then through the system. That's loop 1. The second loop you could pick. You could do pump in through pump 1 in the right direction, then backflow through pump 2, like subtract pump 2. That's a second loop, and that has to work, that to be balanced. Okay, so I jump into Excel, and there it is. Loop 1 minus loop 2 is my second loop. I've got 2 loops, and it covers everything. So then I do the sum of the heads for those loops. They're not equal to 0, are they? This one's too high, that one's close to 0. I square them and sum it, and I want to, guess what I want to do to this guy? I want to minimize it, don't I? by changing what? Q1 and Q2. So we go back to data, solver. This time you just always have to update this. This is the cell that I'm trying to not maximize, but minimize. And which two, I can put them like this, comma, that, or I just messed that up, didn't I? Or I just drag them down. Check this box, meaning they'll be restrained to be non-negative. It doesn't make any sense to have negative Qs through those pumps. So leave that box checked. But sometimes if you're looking, I could get a negative realistic number, then uncheck that box. And then hit solve. And it looks like it went to what I just reported, around 262 total through the system, through the third pump, 109 through the first pump, 153 through the second pump. It's balanced from flows. Well, I forced it to be balanced from flows. And it's balanced for the head gains and losses through the two loops. Look good? Then I had to go back and read the efficiencies. Then I computed the power. What's the power? It's the mass density, volumetric flow rate. That gives me the mass flow rate. Head gain. I know that head gain is the same in foot as in foot pound force per pound mass. And then that gives it to me. I think I needed to put in the divide by the efficiency. That's right. Oh, and then over here I actually converted from GPM to cubic feet per second. So that's a straightforward conversion. And then to get at the horsepower, there you go. So those that calculated 12 by hand, pretty good. And then the next one was at 19 horsepower, and then about 8.2. These efficiencies are pretty low. So if, as an engineer, I would again go look at the diagram just like what we did. Go look at this first one, thank you. It'd say, am I happy with this operating at that point? For pump 1, yeah, I can take it. That's pretty good. For pump 2, I'm a little concerned it's getting away from where it wants to be, but it'll work. It'll work. And then for pump 3, actually, that's okay, isn't it? Isn't that pretty good? So with that, I'm done for today. Thank you very much for your attention.